fully cleaned out my bag this weekend and left my folders at home. I'll have your test on Thursday.
Okay, no problem.
All right, we're going to get started. I know it's a minute earlier, but I'm going to do a couple problems quickly from the Chapter 9 stuff, just because it really does lead itself right into what we're going to be looking at tonight with the Chapter 10 stuff anyway. And I know there was some issues, and I looked, and quite a few people haven't finished the sections yet anyway, so it's not a bad thing to just go over a couple of them. The big thing with a lot of the stuff that we're going to look at, and the biggest thing on the test, because it's not going to say this is from section 9, like on the test, is looking at the problem and trying to figure out what they're asking you for. So most of these problems ends up using some form of the Z-score in it. So being able to find that information and figure out what pieces go into it is very important. So let's look at this one. Production manager at a wall clock company wants to test a new wall clock. The designer claims they have a mean life of 16 years. So they give you your mean is 16 with a variance of 25. So they give you your variance, which is the standard deviation squared. So that means my standard deviation is 5. This is the square root of your variance. Okay, so just keep that in mind. If you see the variance, you have to take the square root of that to find your standard deviation. So they want to know if the sample of 46, so that's n, has a mean clock weight of, actually, sorry, that's in this case, of 17.4. Okay. So we're going to look at our z-score. So I have the 17.4 minus 16 divided by 5 over the square root of 46. Okay? Yes, and as always, your sample size. Any question on where any of those numbers came from? That's the z-score formula. So typically it's just the x minus the mean over the standard deviation. So normally it would just be that part. That's your standard z-form. Since we're looking at sample sizes, we have to take the square root, the standard deviation, and divide it by the square root of the number, the sample size. That changes because now it's your standard deviation for that sample, in essence. Yes.
I was doing the test during majority of first class. What is the n and?
N is your sample size. So in this case, it's 46. And what's the other one? What was the other one you were looking for?
The x. The funny thing.
Oh, that's your mean. That's the mean of the sample. And then my standard deviation divided by square root of 46. And you can type that exactly into decimals as is. So square root and everything. So I get 1.899. So 1.90 actually, this one rounds to, is my Z. Table.
You can just put that in
That, yeah. You can type that in exactly as is. Desmos is your friend. All right, so now we're going to look that up on our z-score. So I go to my z-score table and I'm looking up 1.90 and I get 0.9713. All right, so the question now, we've got our probability. The question is that the one I want, or do I want one minus that? So in this question, it says would be greater than 17.4. So that means it's going to be beyond that point. Because remember, this is from 0 and 2, the 1.9. So we want beyond that, so we're going to subtract that from 1. So the answer to this question would be 0.0287. That's the probability that the mean clock life would be greater than 17.4 years. Do you ever have any item you get die right when the warranty, right, like a month or so after the warranty expires? That's just why. They do their studies and everything else, so they know on average how long a device will last. They then figure out, okay, we want to be able to, we don't want to replace no more than 5% of them. So they set their warranty at that age limit. And they say anything that fails after that point, we won't fix. And they know that the majority of them are going to last like 15 years or 16 years or whatever else, or 16 months, and that's how they do it. That's why everything always seems to fail right after the warranty runs up.
I got a question about the formula. So it's Z equals X minus
The mean
mean divided by standard deviation. What's
divided by the square root of N. So that's why if you looked at what I wrote in the Desmos, see how there's two divisions, there's a division underneath that.
Why did you get the division? Oh, wait, never mind.
I just literally, when you hit the 5, just divide it again, it'll put it underneath it.
Okay, no, my problem.
The one on top, you put the division first. And then you type your numbers in. Because if you type your numbers in,
That's what, yeah.
and then you do divide, it'll only put it under the 16. Yes. Just hit it first. You don't have to worry about that part.
Okay, so is it standard deviation and standard deviation squared, like both those things?
It's the standard deviation divided by the square root of the number, the sample size.
However,
Yes.
Square root of the sample size with standard deviation.
Oh, yeah, absolutely. Yeah. Yeah, you can do it in pieces. Just when you do that, go out like 5 or 6 decimal places. Don't like round it off to really, because the problem is if you round too much, you're going to get a number that's going to not work as easily. So go out a few extra decimal places than you normally would. So, all right. Scientist claims that 7% of viruses are airborne. If the scientist is accurate, what is the probability that the proportion of airborne viruses in the sample of 687 viruses would be greater than 8%? Oh, I forgot to switch back over. There you go. Unfortunately, I cannot. Because it's literally just a screenshot from the thing, and if I make it bigger, it's going to go off the screen. I literally just took a picture of the thing in Hawks. All right, so these are those proportions. So the only thing different, so we still have our mean is the 7%, so 0.07. Your sample mean is 0.08. My sample size is 685. The thing that I need is my standard deviation. And that's the square root of n times 1 minus, or not n, sorry, e times 1 minus p. So that's the 0.07. So actually, I should change that. That's not mean, that's p in this case. And then 0.93. So that comes out to be 0.25515. Now nothing's changed. I'm going to do the exact same thing I just did. I'm going to take the 0.08 minus 0.07 divided by 0.25515 divided by the square root of 686.
So when would we use the standard deviation because there's going to be a formula for it? That's
So the only difference is they put the square root of the 685 in it. I just did it as two steps.
I'm confused when you would use that one versus the other. Because the other
They're
one,
the same.
and then it was like divided by n.
Yeah. So it's that one. It's the same thing. I just did the top and then I'm dividing by the square root of the bottom. The only reason I did it that way is because I wanted you not to have to remember multiple formulas for it. Because in essence, then you can use the exact same formula that's there. Instead of having to remember, okay, I already divided it by the square root of n. I don't need to divide it by the square root of n again. I didn't want you to have to confuse those two things. But it's going to give you the exact same answer either way. So you would just not have to do that extra square root of 360 for that there because you already did it once. So, all right. So let me go back to this so I can type the formula into Desmos and get my answer. So 0.08 minus 0.07 divided by
Was this problem of the 9.5?
yeah. Yeah, this is an Hawks. So when we plug all this into Desmos, we get 1.03. So we go to our Z table, we look up 1.03, and we get 0.8485. Now, do they want greater than that, less than that, greater? So I'm going to subtract that from 1. So the answer is 1515.
I thought you were like, had its points. I remember some talks that you were greater than you were had it twice or something.
So there was one. Hold on, let me see if I can find one. I know the problem. I just got to see if I can find an example of it. All right, so here's actually a good example of it. We can do this one because this will lead into tonight's lesson anyway. All right, suppose a sample of 500 is used to estimate the fraction of voters that favor a particular candidate. If the population proportion that favors a candidate is really 0.4, what is the probability that the error of the estimation will be less than 0.05? So we're saying that the middle, so my P, is 0.40. They want the probability that the error of the estimation will be less than 0.05. So if my error is 0.05, let's say it's exactly 0.05, what would be the high end and what would be the low end? Right. So it can go up to 0.45 and down to 0.35. Okay. So for an error to be less than that, I want to know the percent that's inside those two numbers. Okay. This is the one where you're going to subtract off the outer edges, basically. Okay, so I want to know in between those two values. Yes.
That'd be 0.15.
No, we have to do the Z still. We still have to do that Z score to find on my table. Because remember, everything's that probability. So it's that bell curve. So it's not looking at just exactly a breakdown of the percentages. We got to find the percent that's within that section. So in this case, when I'm doing my Z, we're going to do my 0.0, and we can do, doesn't make a difference, 45 minus 0.40 over, I'll put the full formula there, so this way we can just do it once. It's 0.4, and then it's the opposite, so it's 0.6, and it's divided by 500. Because remember, it's the percentage and then 1 minus the percentage. So 0.4 and 1 minus 0.4 is 0.6. What was the O? Huh? It's, I remember the formula is P times 1 minus P. So if P is 0.4, 1 minus P is 0.6. Those two numbers will always add to 1. Okay? Those two numbers will always add to 1. So the other one was 0.07 and 0.93. Add them, get 1.
The O was figuring out what the denominator was. I
Oh.
was kind of confused, but
And then it clicked.
and then I realized where it was because you were saying something about how you could like you didn't want us to memorize.
Yeah, I did. Yeah, that's fine. And that's why it's, Yes. which I figured that part out after she said that. That's why I just wrote it this way. And when you get this one out, you get the 2.28. So this Z up here is 2.28. What would the other Z be? Negative 2.28. Remember, it's symmetric. This is symmetric, so the Z's are going to be the same. If they were not the same, it wouldn't work. So like if it was down by 3% and up by 5%, I would have to find the two Z scores. In this case, since it's symmetric, I can do it. It's the negative 2.28. So I'm going to look at the negative 2.28 on my Z table because that's going to give me that little piece, which then also gives me the upper piece. Negative 2.28. Yes.
Like if you get 2.2, assume that the other one might be negative.
If they're symmetric across the middle, yes. Like this one, it's 5 on either side. So yes, it's symmetric. They'd be the same. If the error was 3% or 0.03 to the or low and 0.03 to 0.05 to the high, you'd have to get 2%. Two Z's. As long as they're the same, yes, that will work. Probably not, because that's not normally something that happens.
So you're not.
No. No. So I've got 0.0113. So this goes to 0.0113. So is the answer 0.0113? Is the answer 1 minus that? Or is the answer something else? What's the something else? So I have 0.113 down here, right? I have 0.113 up here. Remember, symmetric. Right, I found the negative one. So this is coming from here up to that point. Positive one's going to be the exact same going in this direction. That's the symmetric. If you, I know it does it differently. Yes, you'll get the exact same answer. Yeah. So remember the concept of symmetry. So it's like, and that's why I said if they're the same, you can always look at the negative one and it's going to give you from the right in to your point because of symmetry. So this side, that 0.113, that means coming this direction, it's the same amount on this side. Okay. So I want the middle though, right? So I have to add those and then do what? Subtract from 1. because I wanted the middle section.
0.01.
Oh, you're right. It is. You're right. So we're going to do this. It was there all along. I swear.
That was-
I know, because then I put it when and it's 0. Oh no, that's not. All right, so I add those two up or double it. And then minus 1.
And that's the same thing with finding the two numbers. Table and add them.
Yeah.
Okay.
If you added those two numbers together, it's going to be the same thing. What you could have done, if you had found this number and you had found that number, the problem is you would have ended up with something like, actually, hold on. Not the next slide yet.
Adding the subtracting.
Yeah, so you'd have ended up with this. So negative 2.28 is there. And 2.28 is there. All right, so you found the 0.0113 goes to that point right there. If you had found the other one, 228.9884. From here to there is 0.9884. Since I only want this, I could have subtracted those two and it would have given me the space in here.
Is that not what
It would have been the exact same answer.
Okay, that's what I was thinking.
Yes. Yeah, it would have been the exact same answer. There's multiple ways to get that same point in the middle. The reason why I was showing you this way is that leads directly to what I'm going to be talking about today. Because this is what we're going to be doing. We're going to be doing confidence intervals, which is we're looking at the middle. We want to figure out how confident we are that that's correct. So, all right. First, this is another one of the sections that is stupid and really, really quickly. The point estimate. They're going to give you information. They're going to ask you what the point estimator is. If they give you the mean and ask for the mean, it's just that answer. The only one that I saw that comes up is sometimes they will give you the variance and ask you for the standard deviation. And what do you have to do in that situation? Take the square root. That's it. Okay. So it's another one of those stupid little lessons that you just answer like 5 questions and you're done. But I wanted to give you, so if they're asking you for that point estimator, you're using the mean. If they're asking you for that one, you're using the probability. If they're asking you for standard deviation, you're using the standard deviation. If they give you your variance, take the square root of that. Take a picture because that's literally the end of 10.1.
Yeah, so
All right. Now to the meat of today's lesson. So we're looking, they call it interval estimation. Typically, you'll hear this called confidence intervals. Confidence intervals. So if you've ever, and you're going to see these a ton, and now that I've mentioned this, you're going to notice this a lot in the next year. Because 1 year from now is the presidential election. So literally all that's going to be on the news for the next year and everything else is all the information about the presidential election and the primaries and all that other stuff. So you're going to see polls coming out, and on the bottom, they're going to say plus or minus 3%. That is their confidence interval. So they've done what we're going to do tonight to 90 or 95% confidence. They are confident that their data is correct within plus or minus 3%. Okay, so this is exactly where that information that we're going to get comes from. All right. So if I have a random sample of 100 cars, it has a mean weight of 425 pounds. We want to construct, don't worry about all that. We're going to talk about that in a minute. If the standard deviation of the population is 900. Yes.
So is that mean weight, the sample? Would that be the X with the bar over it?
Yes. Okay. So when we're looking at these, what you want to find is the first thing we need to find is our z-score. So let's look at, I'm not going to do 80%. We're going to do 90 and 95. You almost never see an 80%, and 99% typically is only used in your scientific type studies, that where you really need your data to be accurate. Most of the time when you're going to do typical studies, it's either 90 or 95%. I will show you the other two answers in a few minutes, but we're going to look at those two. All right, so here is the first part of this problem. We need to figure out where 90% is on the bell curve. Need my bell curve. And I can't put a sticky note on the screen. All right, so there's my bell curve. My mean is in the middle. Okay. I want 90% confidence interval. That means that between there and there is 90%. Okay. So what is here and what is here? 10%. Is it 10% on both sides? It's 5% on both sides. So this is 5% and that's 5%. Okay. So what is the z-score for that? So looking at our table, we want to find the z-score that's going to give me 5%. So look at the negative side and find me the one that's going to give me 0.5 or 0.05.
The 0.05
0.05.
and negative 1.6.
Or,
Negative 1.65.
right. This should ring bells because I've talked about this literal exact number before. It's right in the middle, right? And I told you we're typically going to use 1.645. Okay? That was the reason why I brought that up, because this is one of those numbers that you're going to use a lot. Okay? And notice I just put the positive one on the other side. I didn't have to look it up. I know symmetrically it's going to be the positive version and the negative version of that. Okay? Does that step make sense? Okay. We want the confidence interval for that. So what I'm going to do is I want to find the actual number that's going here and here. Okay? I want to figure out how far it's going to be spread. And that's going to be my confidence interval. And say, okay, I know that it's somewhere between this and this. Okay? To do that, we're going to use, did I put that formula? Yeah, and I don't want to give you that yet. So we're going to do this. I'm going to recopy that formula because I don't want to give you the other piece on that slide just yet. All right. So there's my formula. Really complicated, crazy formula that's going to make it really simple by me. That's your mean. That's the z-score that we already found.
Mean plus or minus z-score.
Yep. Times the standard deviation divided by the square root of whatever my sample is.
Times standard deviation.
Divided by the square root of that standard.
You're gonna have
Sample.
to go over that.
I'm gonna. Don't worry. That's the formula. Now I'm gonna simplify it by doing the problem. Remember, what did we do to that number? We took the 90%, we found 10%, and we cut it in half, right?
Yes.
That's what that is. It's, yeah. You'll, in the next table that I'm going to give you that I didn't want to show you yet, this is all going to be made extremely, extremely simple.
It's gonna make sense and happen.
Yes, 99% of stats totally make sense once you apply it to a problem. Because the formulas just look crazy. Like they use the symbols and everything else. It looks really hard. It's not. All right. What is my mean? Mean weight of 425. So it's 425 plus or minus my z-score I found, 1.645. Times, what's my standard deviation? 900. Divided by what's my sample size? 100. That's the formula you just wrote down before. So 425 plus, actually, I'll do the minus one first. Does it look easier now that I did approach numbers? All right. And there is my two numbers.
Wait, what is that solve for?
That's telling you, that's finding you the number that is your confidence interval. So, yes.
If I write like equals, what would the symbol be?
CI.
CI?
Yes. There you go. They actually do use CI. I didn't just make that up, but you'll actually see that one used.
Honestly, even if you made it up,
It works.
I just-
You need an equals. Yes. It stands for confidence interval, CI. All right.
figure out what the symbol for standard deviation is. I still write SD because that makes more sense.
That's fine. All right. So that's the formula that I just had you write down. It looks a lot simpler when you have numbers in it. Okay. We have our mean. We have plus or minus that standard, that's z-score number I found, standard deviation divided by my sample size. So I've got 276.95 to 573.05. So I'm going to write those numbers in, then I'm going to flip back over and you'll see what this actually means. 276, actually we'll round this off to a whole number. So 277 to 573. All right, so this was 90% confidence interval, correct? What I would now state is I am 90% confident that a car's mean engine weight is somewhere between 277 and 573 pounds. Okay? That's what a confidence interval means. Once we figure that out, we can say we're 90% confident that it's between that and that. Okay? So the question is, if I wanted to be 95% confident, is the interval going to be wider or smaller?
Wider.
Because,
Adding 5%.
right, it's going to be somewhere over here and somewhere over here, right? Right. Well, I am. So in essence, I'm stating I'm more confident, but because of the data that I have, that actually means it's a wider range of possible values, because that means I'm eliminating less numbers that it could possibly be. And 99% would be even more wider. I know it sounds counterintuitive. Now I see it, and it's bugging me. The fan is blowing her bandana. You said something, and now that I looked, I'm like, caught it out of the corner of my eye. All right. So here is all the answers for this problem. So, and then I will show you the numbers. All right. So here you can start to see how they spread out. So 80% confidence, I know it's somewhere between 310 and 540. Okay. 90%, I got to go wide. Basically, that means that I'm going to give you a number, and I know 9 out of 10 times it's going to be between those two numbers. Okay. If I'm doing this one, 95% of the time, I'm going to be right. I'm not going to shrink that because that means I'm trying to guess even more. How would I shrink it though? If I wanted to get it small, I would somehow need to have more data, right? And that's what that is. The bigger your N, the smaller it gets. You increase your sample size, I'm multiplying by a smaller number, that makes it smaller. Okay, so if we go back to Desmos, I'll show you. Instead of looking at 100, let's say I looked at 1,000. Now I know I'm 90% confidence between 378 and 472. That's a lot smaller because I looked at more people, or in this case, more cars. If I looked at 10,000 cars, now I'm within 29 pounds. The question is do I need to go that high to get something that's reasonable? Because to look at 9,000 more cars or 99,900 more cars than I did before, it's going to cost me a lot more money to do that data. Is it worth it to make it that narrow? Okay. All right. Write this table down. That right there prevents you from having to look at your Z table anymore to find your confidence intervals. Oh, it would help if I turned the screen, right? Darn it! There, write that table down. It's like it's not there.
And then I think I'm missing something.
No, I'm just going crazy. All right, that is your table. That's your 80%, your 90%, your 95%, and your 99%. Okay, so we don't have to keep going back and looking at our Z table for those specific numbers.
Oh, so the thing on the other side is the Z-score.
Yeah. If you just look, we did 90%, right? What's the Z-score?
Oh,
Okay. Yeah. I allow a no card. I would highly suggest this being on your no card. You're allowed up to a 4x6. That's the bigger size.
I think I asked for thinking bigger size.
They don't have bigger sizes. I don't think they make 5x7 index cards.
No, I
All right. So that is, you won't need your Z table when you're looking for confidence intervals because they're all going to be right there. And the plus or minus is taken care of. Okay. That plus or minus is taken care of because you're doing the plus or minus of that. That's where you're getting the negative side and the positive side of that confidence interval.
So you
You're just going to use that. I don't like that problem. I'm looking for a problem, so give me a second. I didn't like that problem. It was about popping a soccer ball, and I'm like, who really cares about popping a soccer ball? This problem. This is realistic. All right. Paint manufacturers developing a new type of paint. 30 panels were exposed to very corrosive conditions to measure the protective ability of the paint. Think about your car, all right? Coming up with paint for your car. The mean life of the sample was 170 hours or 168 hours before the corrosive failure. Don't think about your car because I'm hoping it's going to last longer than 168 hours, unless they're really sticking it into very highly corrosive areas. The life of the paint samples is assumed to be normally distributed with a population standard deviation of 30 hours. Find the 95% confidence interval for the mean life of the paint. Okay. So, what is your mean? 168. So my mean is 168. What is my standard deviation?
30 hours.
30 hours. Service dog. Okay. What is my sample size? It does. It's just not a number. It's 30 panels. They wrote the word out instead of writing 30. All right. And what's my confidence interval? 95%. All right. So let's write my formula. It's the what first?
168.
The mean plus or minus. What's my z-score?
Oh, the 1.96.
Yep. 1.96 because that's 95%. Times standard deviation divided by square root of the sample size. Huh? Because it's 95%. And that table I just told you to write down says 95% is 1.96. That's why this table is so important. Those are really the only ones you're going to be asked to find. All right. Yes, technically, I could ask you to find 97%, 92%, whatever I want. You don't see those. Those are the ones you typically see. Okay. Unless you're a weatherman and then they look at 50% confidence. All right. One more place than what they give you. So they're looking at 168. So I would round to one more place than that. I don't know what Hawks want you to round to in their problem. So just look at their thing.
You're getting full number from us anyway.
So in this case, it's 168. So I'd go one extra place.
Well, it's 169.98.
Oh, then yeah,
So
it's just
all
170. Yeah, that's fine. So 168 times 6, 30. You did something wrong, I think.
Well, wait, I know what I did.
Okay, I was gonna say because I just did it. Those are not the numbers I got.
I hit parentheses instead of square root.
Oh, that'd be fine. So there you go. So we go from 157.3 to 178.7.
I can't type in this.
So if I'm the one who's creating this paint, and I'm going to give you a warranty on it, I could say that I'm 90 or 5% confident. Actually, I'd be 97% confident that it's below 178.7 hours. So I'm going to say my warranty starts at 178 hours. If it fails after 178 hours, it's on you. Okay. Yep. Light bulbs, not as much nowadays, depending on how old you are. You remember the old light bulbs, it comes up and says 100 hours lifetime on the box light bulbs. Or then you got ones where 1,000, it's like, oh my God, this is amazing. Now friggin' LED bulbs say 50 years. You don't. Actually, what they typically do is they overstimulate the thing, and there's a calculation to figure out how much that voltage changes the lifespan of it. But honestly, nobody's keeping the light bulb for 50 years, so they just throw out a number knowing nobody's ever going to hit it. Technically, an LED should be able to last forever because of the way that the electronic component's created. That's how I took electronics in high school, so I know how those work. All right, so, but that's how they do your warranties. They figure this stuff out. They go, okay, it's somewhere between here. That means I know that's that. Questions with this? Okay. Just like that. All right. I'm going to tell you right now, you will not be able to do 10.2 and 10.3 yet until Thursday. Okay. There's a second part to 10.3 that I'm going to, instead of confusing you today, I'm going to separate the two. There's two different types of tables. There's a D table and a T table. I haven't talked about the T table at all yet. I don't want to start that with 15 minutes left of class. So I'm going to do the part of 10.3 that's actually exactly the same as this, just with the proportions. And then we will talk about the T table stuff on Thursday. So we'll do that separate. I think that's a better way to go about doing this one. No, you won't be able to do 10.2 and 10.3. Because most of there's quite a few questions on there that are directly saying the T tables, and you're not going to have any clue what it's talking about. Because it is quite a bit different. So, all right. Don't do them yet. Wait till Thursday.
Gotcha.
Wait till after class on Thursday. All right. Let's look at this one. So a lot of times you're going to get situations where you're looking for it's a probability type problem. It's like that's the percentages instead of just a specific mean number. And you still want to do a confidence interval. So we know it's between this percentage and this percentage. It's the exact same concept, except that one thing that changes is how we find that standard deviation. It's the P times the 1 minus P piece. That's the extra part that I've got to do. So let's look at this problem. What is my, actually, I'm going to skip a couple things here. What's N? 410. What's my confidence interval? 95%, which means my Z is 1.96. 1.96 and 1.645 you're going to memorize because you're going to use them so often in these problems. All right. What is my proportion? What percentage of people listen to this radio station? No. It says 48 listened to. Out of what? 410. So how would I figure out the percentage? Correct. I'm going to divide them. So it's 48 divided by 410. And I get 0.117. It'd be funny if that was a radio station frequency. Huh? P is basically the mean, yeah.
That's, oh, okay. Never mind.
Yeah, P is basically your mean in it. We don't have a standard deviation in these problems because we actually have to calculate that one. All right, so let's set up my formula. So it's going to be 0.117 plus or minus, what's my Z? Yep. And then times the square root of 0.117 times, well, I guess subtract it from 1. 0.883 over 410. Because remember, for proportions, your standard deviation is that formula for it. Okay. Yes.
Question that we did when we were to us, you had it over 900.
Yep.
900 over the square root.
Of 100, yes.
Why the parentheses, like formula that you use?
So in this one, this is a proportion. So notice how they don't give you your standard deviation. In this problem, they gave you your standard deviation of 30. That's why it's just 30 there. In this one, I've got to calculate that standard deviation, which is the square root of P times 1 minus P. So I can do it as one whole thing, the whole square root. No problem. So I got 0.117 minus 1.96. I'm literally just talking about it as I'm typing it into Desmos. 3 over 410. So there is my numbers. So if I'm let's take this and not talk about a radio station. Let's talk about a podcast. Okay. I survey 410 people. I found out 48 of them listen to my podcast. And I want to get sponsorship for my podcast. I could then say, I'm 95% sure between 8 and 15% of the people listen to my podcast in this area that I did my sample from. Okay. And that could get me sponsorship. Because then they can say, okay, that means approximately 100,000 people or whatever else listen to it based on the general population you're looking at in that respect. So that's how you do this. The bank's going to look at the low end. You're going to look at the high end. Or the sponsor person is going to look at the low end. Say, yeah, you probably got about 9% listening to it. You're going to say, yeah, I have about 15% listening to it. And play around with it. Proportions won't give you the standard deviation. You've got to calculate it. And that's that square root of the P minus, or P times 1 minus P. Yep.
That gives us,
Yeah.
and that gives us the probability.
Yeah.
Which then eventually will translate into the percent.
Yeah. Well, those are probability and percentages are the same. It's like, it's just
Yeah.
it's
but
yeah, it's just how you look at them.
You were throwing out numbers and I was like, wait. You're saying like 15, I'm like, in between
Move the decimal
I
point two
I had
places.
to move the
Yeah.
decimal around.
Yeah.
but Then I realized.
That's the thing. It's like a lot of times you're gonna see like you're gonna get your numbers, and then it's like, how are people really using this? And this is one of those things that a lot of people don't ever talk about. But a lot of the stuff that you do on a regular basis is based on this. Like, this is how they determine warranties. This is how they determine how to finance things. This is how they determine which classes to run. When those surveys and stuff come out asking like, what class would you like to run? Or are you more interested in taking this major or this major? Or they do those workforce studies to figure out how many people are going to go into healthcare in the next 20 years. They then take that data and use it to create classes. And all those studies come back to, in essence, this. All that research and everything else that they do, this is what they're coming out with at the end. All that research is coming up with the numbers to plug into this formula. Okay. So, that's a little tiny. All right, so let's. One more problem, and then I'm going to let you go. All right, find me my answer. You ready?
Can you go back to the gross work?
Mhm.
Okay,
You're welcome.
I
Switch the number. What's the number mean? What's the number mean? So that I'm 95% confident that the average length of stay for an abdominal patient would be between 5.7 days and 7.1 days. So it's basically take the question and use that to formulate an actual statement that somebody would understand. Yes. I tried to find a healthcare one that would, because there's not just you, there's a bunch of people that are like that would click and like where it would actually make more sense. Now I don't know if those numbers are realistic for an abdominal surgery, but it's like
yeah, mine was my N. That's why I asked you to go back.
oh yeah.
Yeah. So I don't know why.
So that's confidence intervals. No. Honestly, the only change between what we did today and what we're going to do on Thursday is I'm not giving you the standard deviation. So that kind of changes how we have to figure out the answer, and that's why we have to use a different table. So
Are we getting another Z table?
you're going to get a T table.
Just so you know, I do listen. And I knew that why I chose 6.20. But I do pay attention.
I know you do.
And then I'm like,
And then what you should have seen when you got your answer is it shouldn't have made sense.
then what he was asking, how come I can't find it on my phone? Because I don't want to use my computer. You know how you added it up?
Oh,
Yeah,
don't. Okay, this is the app.
yep.
You can just sit here. So what is it?
Oh,
I got it here. 6.4. So minus
Mhm.
1.96.
Oh, yeah. So, I mean, obviously. it was hard.
0.996.
Yeah.
And then in this case, we have parentheses.
Yeah, but where was the division?
Oh, it's just divide here right there.
Oh, just here. I think that's what he was asking, the same question I was. Okay.
And then square root 15.
Okay.
And then actually you should. Maybe. Nope. Ah, darn it.
It should be able to copy it.
Yeah, because
Okay.
like I could literally just copy and
that.
paste it
Well, I
and
was
it changed one
debating
thing.
whether to do it on my phone or on my laptop.
So either way,
Did you post Thursday's class online?
I think I did. I will chat.
Also, you said you don't have the tests.
I didn't. I forgot to bring the folder. I will have them Thursday.
Okay.
Because he got a whole lesson today, he's the one who sent them.
You were very nice today. Good boy.
He was not earlier, so I made things in the library, and so he started barking.
Oh,
Because I was like, oh, I scared the dog.
it's not very. He was very good. Have a good day. I'll see you Thursday.
So, yeah, no, yep.
Just like this.
Sorry. Yeah, it's that button right there.
Yeah, no, I was, when you asked it, I was like, I think I'm on this, thinking the same thing.
That's the 19th.
Yes, and then you put the, and then I'll make it, yeah.